At this exact moment while you're reading this, there is a device roughly the size of a compact car drifting through a region of the cosmos that no human has ever laid eyes on before. No probe came before it. No physicist's model ever managed to accurately guess what waits there. And this isn't some cutting-edge piece of modern engineering. It's a relic. It was assembled before the internet was a thing, before ordinary households had computers, before the majority of the researchers currently poring over its data had even been born. Its entire electrical budget is about 4 watts. For context, the little bulb that lights up your fridge draws more power than that. And this ancient, barely powered contraption, originally rated for a 5-year lifespan, is, right now, beaming back information about the universe that is rattling the foundations of modern physics. The scientists analyzing what it sends aren't using words like curious or unusual. They're reaching for words like stunning, confounding, and flatly, we got this wrong. This is the story of Voyager 1. And here's what most headlines leave out. It isn't only what Voyager 1 discovered out there that should worry you. It's what that discovery means for life back here on Earth. It's also what's unfolding with the spacecraft right now, in 2026, that almost nobody is discussing. And it's what's coming in just a few months, a date already fixed on the calendar, marking a milestone no human-built object has ever reached. Stick around, because once you've heard this, you'll never look at the night sky quite the same way. I'm your name, and this is your channel. Hit subscribe if you want more stories like this one. We're only getting started. Let's rewind to where it all began. On September 5th, 1977, a rocket lifted off from Kennedy Space Center carrying a probe named Voyager 1. The mission plan was unassuming. Fly by Jupiter, fly by Saturn, snap some photos, gather a handful of readings, then drift off and go silent. Engineers projected a 4 to 5 year run. NASA figured they'd be wrapping the mission up around 1981 or 1982, a nice little postcard from the outer planets, and then nothing. What actually unfolded is one of the most remarkable chapters in the history of science, and most people have no clue just how remarkable. Voyager 1 refused to go quiet. It swept past Jupiter in March 1979, delivering the first close-range images of that planet humanity had ever seen. It passed Saturn in November 1980 and just kept going, picking up speed with each planetary flyby, using gravity like a slingshot to gain velocity and cover more ground. Before the 1980s were even over, it had already traveled farther from home than anything our species had ever launched. And it was still broadcasting, still gathering data, still running on hardware that today's engineers regard with disbelief. Then, in 2012, 35 years after launch, everything about this story got bigger. Voyager 1 crossed the heliopause. If that term is new to you, understand this. It's the single most significant boundary in our entire cosmic backyard, and passing through it is the equivalent of stepping outside everything our civilization has ever known as home. Picture it this way. The sun doesn't just give us light and warmth. It constantly emits a stream of charged particles known as the solar wind, blasting outward in every direction and inflating a massive protective bubble that wraps around our whole solar system. Inside that bubble sits every planet, moon, asteroid, comet, spacecraft, and living creature that has ever existed. At the outer edge of that bubble, the spot where the solar wind finally loses steam and gets pushed back by the pressure of interstellar space, lies the heliopause. It's the literal edge of our solar system. Inside it, everything belongs to us. Outside it, everything is foreign. In 2012, Voyager 1 punched through that boundary and emerged on the other side. It became the first human-made object to leave the solar system, not symbolically, not on a technicality, but as the first physical thing our civilization has ever placed in the true space between stars. And then it kept talking to us. Sit with that for a moment. Right now, there's a live instrument sitting in interstellar space, not circling a planet, not lingering near the boundary, but genuinely immersed in the cold, ancient void between star systems. A place no telescope, no model, no scientist has ever been able to observe firsthand. And it's sending us reports on what that place is actually like. What it's telling us isn't what anybody expected. Here's where the story takes its first sharp turn. Long before Voyager 1 arrived there, physicists had constructed elaborate mathematical models predicting what interstellar space would look like. Not idle speculation, but rigorous, peer-reviewed theory built by some of the sharpest minds in the field. Nearly all of them agreed on the broad picture. Interstellar space, the plasma occupying the gaps between stars, should be calm, smooth, and thin. A sparse environment where particles drift lazily and little of note happens. A kind of cosmic waiting room. Voyager 1 walked into that supposed waiting room and discovered a storm instead. Beginning in 2017, the plasma wave instrument aboard Voyager 1 started picking up something baffling. A persistent, narrow-band signal. A faint but unbroken hum embedded in the interstellar plasma that, according to every existing model, simply shouldn't exist in the form it does. This wasn't a one-off blip easily written off as instrument noise. It was a continuous emission, repeating year after year, spanning a stretch of interstellar space over 900 million miles across. For comparison, Earth sits about 93 million miles from the Sun, so this signal has been tracked across a distance roughly 10 times that gap. Researchers who published their findings in the peer-reviewed journal Nature Astronomy didn't mince words. Interstellar space is not the calm, uniform void the models promised. It's turbulent. It has structure at every scale, from distances you could measure in meters up to spans measured in millions of miles. In a very real sense, it's alive with motion and complexity that had been completely hidden from us, simply because no instrument had ever been stationed inside it before. Pause on that for a second. Every single model of the universe beyond our solar system was constructed from the outside, from a planet, using telescopes, math, and theory. Now, the very first device we've ever physically placed inside interstellar space is telling us those models missed something fundamental, that everything beyond our solar system is messier, more dynamic, and more layered than we understood. But here's where this stops being abstract and starts hitting close to home, because these findings about interstellar space don't just stay out there. They reach back to us. The same bubble separating our solar system from this turbulent outer environment is the very bubble shielding life on Earth. The heliopause isn't just a line on a diagram, it's a shield, one that deflects the most dangerous cosmic radiation, the high-energy particles streaming in from distant supernovae, keeping them from slamming into the inner solar system at full force. If that shield turns out to be weaker or less predictable than our models assumed, the implications for biology on Earth are enormous. And what Voyager 1 is telling us is that the interstellar environment pushing against that shield from outside is more turbulent, variable, and energetic than any model ever accounted for. We don't yet know precisely what that means for the shield's long-term stability. But simply having to ask the question represents a shift in how we understand our own vulnerability as a species. Now the story takes an even stranger turn, because in 2023, Voyager 1 very nearly died. For 5 straight months, the spacecraft kept transmitting a signal to Earth, but the content was gibberish. Corrupted, scrambled code that the engineers at NASA's Jet Propulsion Laboratory, despite decades of reading everything this probe had ever sent, simply could not decode. The instrument was alive. The signal kept arriving. But whatever message it was trying to send had become unreadable. For a team that had run this mission successfully since 1977, nothing like this had happened before. When they finally traced the cause, it was both mundane and alarming. A single memory chip within the spacecraft's flight data system had physically degraded after nearly 5 decades of relentless cosmic radiation exposure. One tiny component, a fraction of an inch across, had developed a fault corrupting the very software responsible for formatting and transmitting the science data. No alarm triggered, no warning arrived. The chip had simply worn out after 46 years of continuous operation in the harshest environment any human-made object has ever endured. Normally, you'd fix a broken part by traveling to it and swapping it out. Here, the component sat roughly 15 billion miles away, with no repair mission conceivable on any relevant timescale. The only tools available were radio waves, and even those needed 22 hours to travel one way. Every diagnostic attempt, every probe of the problem, every proposed fix demanded a minimum of 44 hours for a single round-trip exchange. Picture what that actually felt like inside mission control. You study the data, form a hypothesis, draft a set of test instructions, transmit them, then wait 22 hours. You get a response, analyze it, discover something you didn't expect, form a new hypothesis, write new instructions, transmit again, and wait another 22 hours. Repeat that cycle patiently for months, all while knowing that a single wrong command sent across 15 billion miles of empty space could end the mission permanently, with zero chance of recovery. The JPL team worked through it methodically, under a kind of pressure most engineering projects never encounter, and they pulled it off. They determined the corrupted code couldn't be repaired outright, but it could be relocated. They split the damaged software into smaller chunks, distributed those chunks across different sections of the spacecraft's remaining memory, individually verified and rewrote each piece to function correctly from its new address, then carefully stitched everything back together. It was, in effect, remote brain surgery performed through a 44-hour communication lag on a nearly 50-year-old machine 15 billion miles from home. By mid-2024, Voyager 1 was back online, transmitting clean, complete, readable science data once more, and almost immediately it resumed sending more evidence of those unexplained plasma oscillations out in interstellar space, more measurements of turbulent structure no model had ever predicted. A spacecraft that should have died in 1981 had clawed its way back from what could have been permanent silence. And it came back with more to tell us. Still, none of that, not the discovery, not the near-death experience, not the recovery, prepared anyone for what Voyager 1 had actually found the moment it crossed the heliopause back in 2012. Because this part of the story is described in scientific papers using language that stops sounding like physics and starts sounding like something else entirely. For decades, models of the heliopause predicted a gentle transition, solar wind gradually thinning on the inside, interstellar medium gradually appearing on the outside, a slow blend at the edges, like a river easing into the sea. That is not what Voyager 1 encountered. At the heliopause, particles weren't calmly fading away. They were colliding at speeds approaching a meaningful fraction of light itself, smashing into one another with enough energy to generate temperatures near 30,000 degrees Celsius, not inside a star, not near a star, at the outer edge of our own solar system, in a region theory had described as cold and empty. Some researchers have called this zone a wall of fire, and not as a metaphor, but as a genuine physical concentration of ultra-energetic charged particles forming a real barrier at the edge of everything we call home. Then came the magnetic discovery. For decades, one core prediction about the heliopause was that the magnetic environment would shift dramatically at the crossing, the sun's magnetic field on the inside, the galaxy's entirely separate magnetic field on the outside, two distinct domains meeting at a clean boundary. Voyager 1 found something else entirely. The magnetic fields on either side of the heliopause were, in ways theory hadn't anticipated, linked together. The sun's field lines, stretched outward by the solar wind and compressed at the boundary, were interacting with the galaxy's magnetic field through a process called magnetic reconnection, where field lines from separate sources rearrange and release energy. Our solar system and the surrounding galaxy are not magnetically isolated from one another. They're connected. At the very edge of everything we know, energy is being traded between our home and the wider cosmos in ways no pre-Voyager model ever accounted for. This isn't a minor footnote. If the relationship between our solar system and interstellar space is this dynamic, connected, and energetic, then our understanding of how the heliosphere has shielded Earth across geological time may need to be rebuilt from scratch. Now let's turn to what's happening right now, in 2026, because this story isn't finished. In fact, it may be entering its final act on a tighter timeline than most people realize. Earlier this year, NASA made a call nobody on the mission wanted to make. The low-energy charged particle experiment, one of Voyager 1's instruments that had been gathering data nearly non-stop since 1977, was powered down. Not because it broke. It was working fine. It was shut off because Voyager 1 is running out of power, and there simply wasn't enough left to keep it going. Voyager 1 draws its electricity from 3 radioisotope thermoelectric generators, essentially containers of plutonium-238 that produce heat as the material decays, heat that gets converted into electricity. At launch, these generators put out about 470 watts. Today, nearly 49 years later, they manage roughly 250 watts, losing about 4 watts a year. Sometime in the early 2030s, output will dip below whatever minimum is needed to run even a single remaining instrument, and Voyager 1 will go permanently silent. The mission team has seen this coming for years and has carefully mapped out which instruments to shut down and in what sequence, trying to squeeze out as much science as possible from a shrinking power budget. Of the 10 scientific instrument packages the probe launched with, 7 have already gone dark. These are some of the hardest calls a science team ever makes. Every instrument switched off represents questions that will never get answered, and there's no way to flip one back on once you've decided you cut power too soon. Here's the twist almost nobody outside the JPL team is talking about. They haven't given up on buying more time. Engineers are currently testing something reportedly nicknamed internally the Big Bang procedure, an experimental restructuring of how power flows across Voyager 1's remaining systems, aimed at squeezing extra electrical capacity out of components currently running below their potential efficiency. It's technically risky, since even minor changes to power distribution on a nearly 50-year-old spacecraft with no manual override could produce unpredictable results. So the team is doing what careful engineers do, testing it first on Voyager 2, which has somewhat more available power and sits a bit closer to Earth, making any failure less catastrophic. Those tests on Voyager 2 were slated for May and June of 2026. If they prove the procedure works safely, the same fix could be attempted on Voyager 1 as early as July of this year. And here's why that matters. If it succeeds, there's a genuine chance the low-energy charge particle instrument, the one just powered down, could be switched back on. The team is being cautious, making no promises, but they're still trying. Because with Voyager 1, betting that the story is over has never once paid off. And now, the date already locked onto the calendar, one no human civilization has ever reached before, and one arriving whether or not anybody notices. On November 18th, 2026, at 2:16:12 a.m. Pacific Standard Time, Voyager 1 will reach a distance of exactly 1 light day from Earth. At that point, a signal traveling at light speed, the fastest anything in the universe can move, will take a full 24 hours just to reach it. Send a command Monday morning, and you won't know it arrived until Tuesday morning, with the spacecraft's reply not landing until Wednesday morning. 2 entire days just to complete one exchange. No human-made object has ever been that far from home, not once in our species' entire history. On that day, Voyager 1 will cross that threshold for the first time while still alive, still transmitting, still sending data back, and then it will simply keep going. Every passing hour carries it roughly 38,000 more miles deeper into interstellar space. The communication delay will keep stretching, the power supply will keep shrinking, and sometime in the 2030s, the final signal will arrive. Even then, Voyager 1 won't stop. There's nothing in interstellar space to stop it. No friction, no atmosphere, no gravity strong enough to meaningfully bend its path. It will simply keep gliding, silent, in a straight line at 38,000 miles per hour, into a darkness with no end on any timescale humans can grasp. And bolted to its frame, riding along with a dying machine, is something that will outlast every part of it. The Voyager Golden Record, a gold-plated copper disc carrying greetings in 55 human languages, the sound of rain over a forest, the crash of ocean waves, the sound of human laughter, 90 minutes of music drawn from cultures across the span of human history, diagrams laying out the basics of our physics and math, and a map built from pulsar positions meant to show whoever finds it exactly where our planet sits in the galaxy. Carl Sagan, who helped design the record, once called it a message in a bottle cast into the cosmic ocean, and that's precisely what it is. Whoever or whatever eventually finds it, another civilization a million years from now, or some form of intelligence we can't yet imagine. The record will tell them something true, that a species existed here, that they were curious, that they reached outward, that they built something out of metal and electricity and mathematics, and sent it beyond everything they'd ever known, carrying the sound of their own laughter along with it. That record will still be drifting when the sun swells into a red giant and swallows Earth's orbit. It will still be moving long after every human city, every archive, every name we've ever carved into stone has been ground away by time and geology. It may be the single most enduring thing our civilization has ever produced, and it's riding on a spacecraft currently running on less power than the bulb above your bathroom sink. Let's return to the science, because there's one more piece of this that belongs at the center of the story. That persistent plasma emission detected since 2017 isn't just a curiosity. According to the researchers studying it, it's the first continuous real-time measurement of interstellar plasma density humanity has ever recorded. Before this emission was detected, scientists could only capture scattered snapshots of plasma density out there, triggered by specific events, like the shock waves from massive solar eruptions rippling all the way out to the heliopause and beyond. Useful but sporadic, like trying to understand a continent's weather by checking one thermometer in one city once a year. What this ongoing emission offers instead is something closer to a live feed, a continuous portrait of interstellar plasma as the spacecraft drifts through it, day after day, year after year. And that portrait shows us that interstellar space isn't some static, uniform backdrop. It has texture, it has weather, it contains structures built from charged particles and magnetic fields stretching for millions of miles, interacting with our solar system's outer boundary in ways no Earth-built model ever detected or foresaw. The space between stars isn't empty. It's full, active, possessing a physical character we are only now, for the first time in human history, beginning to read. There's a question at the heart of all this that scientists haven't resolved yet. The persistent emission has two competing explanations, and researchers analyzing Voyager 1's data haven't determined which is correct. One possibility: it's thermally excited plasma oscillations, the natural vibration of particles interacting with their environment. That would be a genuinely important finding, but one that fits comfortably within existing physics without demanding a rebuild. The other possibility: it's something called quasi-thermal noise, a different physical mechanism carrying density and temperature information in a subtly different way, one that would force a substantial revision of existing models of the interstellar medium. Settling the question requires either more data from Voyager 1, which produces less of it every year as more instruments go dark, or an entirely new mission purpose-built to study interstellar space. No such mission currently exists. None is currently funded. Even if one were greenlit, built, and launched today, it wouldn't reach the heliopause for at least 25 years, which means that when Voyager 1 finally falls silent, this question will remain unanswered. The map it began drawing will simply stop updating, and the only real-time window our civilization has ever had into interstellar space will close, likely for decades. That silence is coming. We don't know the exact date, but we know the direction. Every year the power drops a little more. Every year, another instrument goes dark. Every year, the JPL team faces harder decisions about what to keep alive and what to let go. And sometime in the early 2030s, the last instrument will slip below its minimum power threshold. The final signal will begin its 24-hour trip home, arrive, and be recorded. And after that, nothing. Voyager 1 will simply keep moving, silently, at 38,000 miles per hour, carrying its golden record through the dark. Passing through regions of space human eyes won't reach for tens of thousands of years, continuing a journey that began one September morning in 1977, when a group of engineers aimed a machine at the stars and pressed launch, expecting it to last 5 years. Here's what I want you to sit with. Buried in the middle of this story is a fact that's easy to overlook once you're caught up in the physics and the engineering drama. Right now, in 2026, the only living scientific instrument humanity has ever placed in interstellar space is 48 years old. It runs on technology older than the personal computer. It's powered by less electricity than the bulb over your kitchen stove. And it's rewriting how we understand the universe and our place inside it. We've since built things far bigger, far more powerful, far more expensive, and far more technologically advanced. And none of them have told us what Voyager 1 is telling us right now, because none of them had the one thing Voyager 1 had: the sheer persistence to keep going long enough to actually arrive. Some questions about the universe can only be answered from inside it, not from a ground-based telescope, not from an Earth-orbiting satellite, not from a mission to Mars or the asteroid belt, only from a machine that crossed the heliopause and entered the true space between stars. We have exactly one such machine. It's old, it's dying, and it runs on 4 watts of power. As long as it keeps transmitting, we need to be listening, because when it finally falls silent, the answers to some of the biggest questions we've ever asked will fall silent along with it, at least for a generation. The signal is still coming, stretched across 15 billion miles, delayed by 22 hours in transit, carrying word of a universe stranger, more turbulent, more interconnected, and more extraordinary than any model built from the ground has ever gotten right. One machine, 4 watts, one chance to listen. The only question left is whether anyone's actually paying attention. If stories like this are what brought you here, subscribe now and hit the notification bell, because next time we're heading even further into the edges of what science actually knows. Drop a comment telling me what surprised you most, and share this with someone who needs to hear it, because this story deserves a lot more attention than it's currently getting. Thanks for watching.